Okay, this is our fourth and final video for replacing the Electa carnage. But also this will be a good place to review about the quantum stuff. So in our so I'm going to recommend this video for those of you who aren't going to review the whole thing, just to talk about the quantum stuff. All right, so in the last video I said I really recommend that you go through and look at this Bozeman Science by a guy named Mr. Anderson. He talks about why the analogy of the marching band for refraction of light. This change of the angle when you go from one medium to the next. What he has here is, here's a marching band going along on a street where they can march just fine, and they hit sand, and that slows them down. This is called Snell's law. For my class, you're not going to need to know a terrible great amount of Snell's law, but later there will be a jello optics thing where you will create this once you have your lasers from me at home. Oh, and I just saw, have I apparently, no, it is published. Oh, I have two Snell's law things. Okay, so here's our refraction of light. So do go and review that so that you understand Snell's law. But you can wait, if you're not that interested, you can wait until we do our jello optics. So we're going to spend next unit a lot. My main focus of next unit is I was taught a lot that the speed of light is the ultimate speed limit for the universe. And I think when they were covering it in 802, I don't know, I just didn't get it, or I wasn't there that day or something. But I wasn't really, I'm like, okay, other people are convinced, I guess I'll be convinced. But what I want to do is walk us through why we're convinced by the math that the speed of light is the ultimate speed limit for the universe in our next unit. So we're going to spend a lot of time talking about light doesn't ever speed up. But does it ever slow down? That's a great question. So the Muggle answer, and I don't mean Muggle in a dismissive way, it's really important to do well on your AP Physics exams. Please give the Muggle answer when you know you're taking a Muggle test. The Muggle answer is yes. It is only going 299,792,458 meters per second in a vacuum. That is the answer to have on the test. It goes slightly slower in air, it goes much slower in glass. Different things have different refractive index. But there's a problem. Because a photon, and we're going to talk about light is both particle and wave, the photon, the particle of light, never goes any other speed than the speed of light in a vacuum. In a way that makes sense. We talked about this diagram when we were talking about spectral emissions, and we're talking a little bit about Max Planck. We will return to that because I think we're a little bit shaky on it, but we will return to that again. And if you think about what we had here, is we send in some radiation, some energy, to interact with an electron. And that electron pops up to the next orbital shell in a quantum leap, which means it is never in shell 2.5. It's either in shell 2 or it's in shell 3. It could be in shell 1 or shell 2, but it's never in between. And this is what we think of as a quantum leap. So it's going to pop up to the next one, and then when it relaxes down, back down to its natural state, it's going to release a photon of light. And what that photon is going to encounter is mostly empty space, right? So the photon that it releases is definitely traveling the speed of light. So inside matter, what is going on is a little bit weird. Why this actually happens. We can say that waves slow down, and we see physical waves slow down in different media. But as we're going to find out with the Michelson-Morley experiment, light doesn't have a medium. So this is where we get to my, I always shoehorn in Harry Potter. So there's this wonderful thing when Hagrid says, "You're a wizard, Harry." Our Hagrid is not Hagrid. Our Hagrid is going to be Richard Feynman. And Richard Feynman has a lecture that I will find the clips for you and edit down for you guys, that is describing how refraction of light is a quantum effect. Light does refract. So light through air is going to change, and we see this. Spearfisher people have known this for many years. They have known that when you are spearfishing for fish, the fish is really here, even though he appears there. So this is something that isn't just something first observed by modern man. We see it when we pass it through glass or jello optics. When we pass light through a prism, the different wavelengths of light have different phase speed. Not different transverse speed, different phase speed. And they slow down differently as they pass through a medium, as they pass through something, when they're going to do this quote-unquote slowing down. The slowing down that they do in their phase will change where the red light comes out, where the green light comes out, all that sort of thing. So this is how there is a quantum effect that helps that prism that you made out of a mirror and a little bit of water. There is a quantum effect going on that causes things with different phase speed to slow down in different ways. Okay. And this kind of indicates that there's going to be a problem with the Snell's law and the Muggle answer, right? Because we know that there's different phase speeds affect how things come out, but they come out with the same group speed. That is, if you put this pulse of light in, when you see the pulse of light come out here, the group of light that came in is going to be in different locations, but they're all going the speed of light when they come out, and they all took the same amount of time going through. So there is kind of an indication that maybe there's kind of a problem with the Muggle answer of light just slows down and it's simple. It's not simple. When we get around to using this cat and figuring out that E is equal to mc squared, and we're going to derive it using, this is kinetic energy, it's that 1/2 mv squared that we used in our Newton's cradle homework. So that all that stuff is not busy work. This is all stuff that, and we're going to come back to potential energy like crazy. When we figure this out, what we observe, the cat, the light that we observe from the cat, and our distance going away from it, is going to result in something known as the redshift, because the speed of light, the group speed of light, will always be the speed of light and in a vacuum. And so through the vacuum of space, because of the change in our relative positions, we're going to see a shift in the apparent wavelength of light. So associating the wavelength and frequency of light with the energy it contains is going to be a very important piece, and I hope it will be worth going through all of this wave stuff that we're learning and unlock some of the mysteries of some Muggle answers that may be fine for Muggles, but eventually, should give us a little bit of trouble. We've got to learn to operate in the Muggle world, but then we come back and we get to the bigger answers in a bigger way. And I guess the reason I keep coming back to Muggle as an example is you'll run into teachers, very well-meaning teachers in your life, that that will say, well, this is just it. It's Snell's law. Memorize it. And they really do have a point. They have a concern for you that, this is what you need to accept, and you have to get through freshman physics, AP physics to get there. And we need to be able to do all those things. But every once in a while, you'll find someone who's also a wizard, and you'll be able to ask these things and talk about these things. And sometimes don't take it too harshly when people don't understand the questions that you're asking. Feynman found the same thing. We'll talk about a time when he asked Niels Bohr a question, and Niels Bohr assumed that he just didn't know what he was talking about and started explaining very basic things to him, and Feynman was really embarrassed. So this happens a lot. But a cool thing, and for your homework, is that, and we'll talk about it next week, is that the Rayleigh effect, which you'll see in your homework, is caused by all this stuff happening together. Interference, non-interference, phase shift, all this kind of stuff, and we see it when we blow bubbles, we see it in the blue sky, we see it all around us. So quantum is surrounding us in the life we live. All right, see you next week. Bye.